Yeah, it looks great.
Looking good on my end.
Awesome.
Okay.
Yeah,
So,
mine too. Yeah, you're good.
okay. So Paula asked for some information about the PRIMo model. So that's the gist of this talk. And a little bit of motivation that's been driving our research that flood impacts are especially concentrated in urban areas and growing quickly. There's a report out. The Senate had this interesting report that they're now saying that like flooding's costing us 1 to 2% of GDP, which I thought was a pretty powerful statement. And these flood impacts and our responses tend to reinforce socioeconomic inequalities. So flooding is one of those things that's contributing to not only impacts, but these disproportionate impacts that further sort of strengthen these inequalities we have in the US and other places, but US especially between the haves and the have-nots. Um, and so research points to the really importance of, flood risk assessment and working towards solutions in a way that is, collaborative and engaging communities, understanding what's at risk, trying to come up with solutions that align with preferences and needs. But the reality is that participation is really challenging. Um, it's if you've gone through an adaptation planning process, it's a slow process. The people that are most vulnerable can't afford to show up at meetings and share their time. They have to go to work. Um, and one of the things we've identified in our work is that the modeling itself really can contribute to like a procedural inequality, which is sort of this diagram on the shows two different sort of models with which like flood simulation can support an engagement and decision-making process with stakeholders. And on the left-hand side is what we most commonly or routinely do today, which is there's some lead stakeholder, Army Corps, Texas Water Board, a flood control district, whatever it might be. And they work to develop a simulation technology and sort of imagine climate scenarios and create a bunch of models. And then you go through like an engagement process where, community stakeholders have access to that information, provide feedback, and then that then goes back and sort of provides feedback on the scenarios and so on and so forth. But what often happens is that many decisions end up getting made before to the point that the stakeholders feel like they're really not in a position to really substantially influence outcomes. They're kind of just nibbling at the edges of decisions. And so we've sort of hypothesized this on the right-hand side that if you could have like a more fast response platform that was accessible to many stakeholders, you could get more people involved in like exploring risks and how to manage them. More people can be involved in saying, well, what if I raise levees, or what if I invested in green infrastructure, or whatever it might be. And you can sort of spread that learning out across more people. And one thing we sometimes lose track of is that the modeling process that we have the privilege to do as engineers is a really amazing learning exercise. You see, like, as you model what seems to be beneficial and what isn't, and then and so one of the motivations here is to sort of share that learning across a larger number of people. How to do that exactly is unclear. We have an NSF project funded in Florida where we're testing this out. So the idea is to kind of test out this more sort of fast response approach. So in our research, I guess the fourth bullet point here is we're advancing this dual grid modeling approach to create like a faster, more interactive flood simulation that could be, more responsive than many of the models we have today. And we were testing this idea of collaborative flood modeling, for more effective projects, more equitable projects, and maybe even faster timelines. A lot of times, just because there's so many decisions that need to be made, people that need to provide input, regulators that need to check off on projects. I mean, the extent that all that could be more interactive and fluid does offer the potential maybe to speed up some of the timelines of projects. And then the third aspect is trying to develop flood infrastructure solutions that offer multiple benefits, benefits beyond flooding. I mean, historically, a lot of flood infrastructure was designed to prevent losses, to provide safety to people, which are really important goals. but unfortunately at the expense of other benefits. Like in California, we have all these sort of concrete canyons that sort of send floodwater racing to the coast, and there's no shade from heat waves. There's no water, really poor stormwater capture. We're starving our coastline of sediment, and so that infrastructure design was excellent, has proved excellent for flood protection, but it really is lousy from a broader multi-benefit perspective. So how do we get more natural functions back into our flood infrastructure and the ecosystem services that come from those functions? So that's kind of been the gist of our work. And a lot of my our experience was shaped by this study we did in or 15 years ago. We studied like this Baldwin Hills dam break test case. And I still feel it's one of the very few like um, cases of a flood that was fairly well mapped, like knowing what was the flood extent from an urban flooding situation. So in 1963, there was this water supply reservoir that sat here where the red star is, and it was engineered with like an embankment and this asphaltic liner around the side. And it was meant just to store water for Los Angeles Department of Water and Power. But due to oil and gas exploration underneath these hills, there was differential settlement underneath this reservoir, and there was a crack in this asphaltic liner. There was basically water started seeping into the crack, and there was a piping failure. And on the photos on the left, you can see that there a hole opened up, and then people tried to throw stuff in it, and it didn't work. And eventually, the flood gave way, and we have a map of what flooded in that area. So so with this, you could say, well, how well can we predict like a really fragmented flood zone like this, where you can clearly see that like the street grid is shaping like where flooding goes and is a really important input into understanding and predicting urban flooding. And to build a model, we used a two-dimensional shallow water model and a 3-meter resolution grid to try to capture that detailed topography. And we had information, we sort of built a land use model so we could kind of assign different manning ends to different areas. And we also had data on where all the storm drained inlets were that would potentially capture some of that water and then route it to this flood channel. And on the graphic, I have a bunch of maps of the maximum flood extent predicted by the model for a number of different sort of scenarios that helped us learn about the sensitivity of models to different data inputs and grid resolution and things like that. So even though this flood took place in 1960s, there was a LiDAR survey done in like around 2006, I believe. And we used that LiDAR survey. So it was over 30, 40 years after the flood, but the street layout hadn't changed a whole lot. So it seems like there was fairly good stability in the topography. It's not like they came in there and regraded it or totally reshaped the land surface. So the white, you can barely see a white line here, but the color contours here show contours of depth. And this is sort of a base case in the top center here, where the topography is based on a LiDAR-based digital elevation model. We ran the model at 3-meter resolution. We start water up here, it runs down the hill, spreads out, collects in this channel. And then we did like what you typically do as a numerical model. You say, well, if you make your mesh finer, do you still get the same answer? And so we went with like even finer mesh, which was closer to, I think, 1.5-meter resolution or something like that. And it changed a little bit, but just, not a lot. We made our model coarser, so we went to like I think it was closer to like a 10-meter or 9-meter resolution mesh. And then you start seeing pretty substantial over predictions, and you can see the way it kind of smooths out as you go from to a coarser mesh. You start smoothing out the flood zone, and it kind of looks like a bigger pool and less sort of you don't sort of, for example, differentiate these individual flows along streets anymore. They kind of become just one sort of pooled area. So that informed the thinking we still have today, which is that to do a decent job of urban flooding in areas where there's sort of relief defined by the grid network. So if the streets are graded such that the streets sit lower than the land parcels, which is true in many cities, then you would think you'd need like a nominally like 3 meter resolution to sort of resolve those features. We also explored like the benefits of different input data. So we'll take this 3 meter resolution mesh, but now what if you parameterize that with different sources of elevation data? So in this case, we coarsened our digital elevation model to 9 meters and reran the model at 3 meters. And it's somewhat similar to what you get just by coarsening the mesh. Also some significant over prediction. So this is now like so imagine like a 9 or 10 meter digital elevation model trying to resolve flow along these narrow streets, and it's not as sharp. We also grabbed what was available at the time as the national elevation data. I mean, that's a living resource that evolves over time. But at the time, it was that digital elevation model didn't show any sort of topographic features representative of the street network. And so it predicts a pretty smooth flood zone that actually spreads out quite a bit further than the observed flood zone. And then globally, sometimes the best available information is like an SRTM DEM. At the time we did this study, like, that was one of the only globally available DEMs. And you can see that gives a really, odd representation of flooding. And that's a 30-meter data product in the US. Okay, so the takeaways, from this Baldwin Hill study, simple takeaways was that, if you want to do a decent job of urban flooding, you're going to have, access to a LiDAR survey that captures the topographic relief of the road network and features like that are going to shape where flooding goes. 3 meters seem to kind of, strike a decent balance between accuracy and computational cost, which is always like the million-dollar question. You can always go finer or maybe a little coarser and do okay. So that's kind of the thinking there. And also, I didn't emphasize this in these slides, but if you took out all these storm drains, you would also overpredict flooding. So when we didn't have storm drains in the model, then the flood zone wasn't as tightly captured. And we, in fact, to get this level of agreement, we calibrated a discharge coefficient for the storm drain inlet flows. And it came out to a number which was within like an acceptable range of like 0.5, something like that. So that was kind of the lesson there, a little lesson about like how do you do, what matters to get urban flood models to be more accurate. But then the model we had been working with, it was called like this model was called we called it PRIMo, but it was a 2-dimensional shallow water model on an unstructured grid that could allow you to refine some areas, finer and other areas coarser. And I just decided that as we went to bigger and bigger scales, like the unstructured data format was just too much of a pain in the neck. At really, really large scales, like for just saving data formats just become more, I think, important than the computational method. So we shifted towards a raster-based approach where you can really store information much more efficiently and just operating on raster grids. But this model is designed to really use 2 different grids. It has this dual grid model structure. So we have information from a digital elevation model on a fine grid, but then we use that every time step to make an estimate of the exchange of mass and momentum between neighboring cells, and make a solution update on a coarser grid. And then once we have that solution updated to the coarser grid, we sort of project it back down to the finer grid to make estimates of the fluxes again, and that happens every time step. The method's explicit. It tends to scale well on CPUs, and we've been running it more frequently now on GPUs. And we've also been investing in sort of approaches to handle infrastructure like levees, storm pipes, reservoirs, pumps, things like that, to try to have a model that's fast and can approximate, the features of urban areas that are important to get flooding right. So this is a diagram meant to illustrate how the model works. So the grayish boxes, imagine that's your fine grid of elevation data. So there's one elevation data at every one of those boxes. And then the red box is the course grid, where you're going to do a volume balance and a momentum balance in the x direction and a momentum balance in the y direction each time step. And you can imagine that inside of each one of these red boxes, there's a free surface elevation. And that free surface elevation is not assumed to be horizontal. It's allowed to slope. So it can slope in the x direction and slope in the y direction. So the idea is that you have a free surface and a slope in each cell, and then you can reconstruct what the free surface elevation is for all of these small boundary cells. And you could subtract the depth in the little fine grid from the free surface elevation resolved in red, and then estimate a depth for every one of these boundary cells. And then you compare that with the depth on the other side. And then we assume that velocity is spatially uniform across each of these coarse grid cells. And so we reconstruct that on every little edge like this, reconstruct that, estimate a small little flux for that tiny little edge, and then we repeat that for all the edges around all sides of the model. And then you end up with like a explicit update equation where you sum up all the little fluxes on each side, the left side, the bottom side, the right side, the top side, and off you go, advancing the solution in time. So that's the essence of the dual grid method. You take a coarse grid, you sort of assume the free surface is sort of sloping, reconstruct depths around the edges, compute fluxes so you get exchange of mass and momentum between the boundaries, advance to the next time level, and then repeat over and over again. And the operation count for a conventional method on an n by n grid would be like n to the third power. But with this upscaling method, you knock that down by a factor of the upscale factor squared. So basically, if you're using upscale factor 10, then you could cut your operation count by a factor of 100, which helps a lot with runtimes. And then if you took this method and did like very traditional testing of a numerical performance, you could sort of see that it works well. Like up here, I've got a classical dam break problem where you've got a channel that's 1 kilometer long. On the left-hand side, you've got like a water level that starts off, say, at some height, and then here it's dry. And the red curves, or the gray curves here, show a solution advancing in time. So you get a dam break wave that moves to the right, and you get a depression wave that kind of moves to the left. And so if you just run this model where the coarse grid and the fine grid are the same, that's a classical like explicit method. You get a little diffusion of the wave here and here, but it reproduces the wave. So now if we go to in the velocity, you'll have some error of the velocity at the tip, but you get sort of a monotone solution. But then if you start upscaling, then you add a little bit more diffusion. So this upscaling method will give you a solution that's similar to coarsening the grid. So you can kind of anticipate but better than what you'd get when you start having variable topography. And so then in that paper, we kind of revisited the Baldwin-Hills test case and asked, well, how well would PRIMo do in that test case? And we tested it with an upscale factor of 2, which means the size of the red cells are twice the size of the black cells. And we tested it with 5 and 10 and 20. And we could see that like going from 2 to 5 to 10, there wasn't a whole lot of change in the performance of the model. You still got greener areas where the PRIMo model agrees with the observations of flooding, and then red are areas where flooding was underpredicted, and blue is areas where flooding is overpredicted. So we found that like we could go from upscale to a factor of 10 and still capture that flooding fairly well. And we could also put the same storm drains into the model and as we did in the previous model. But then if we started going beyond 10 up to 20, we started seeing that like the model was over predicting flooding. So there are limits to like how much you can upscale, just as there's limits to how much you can coarsen a grid before you lose information. And then now we sort of this is just like an animation showing like a river in Georgia where we have PRIMo routing flow down a sort of a really curvy river. And what kind of blows my mind is that even though the method may only have like one or two coarse grid cells across a channel, it still does a decent job of resolving flows through the channel. So on the left-hand side, you get this fine resolution visualization because you have the fine resolution, grid available. But the mass and momentum balances are done at this coarse grid shown on the right-hand side. And that's sort of the coarseness with which we've done the sort of the volume and momentum balances, um, and uh, and so it seems like a really nice trade-off between computational effort and cost and so on. Okay, so then one of the big weaknesses of this dual grid method is that you're only sampling information along the perimeter of a coarse grid cell when you compute the fluxes, the way I've done the method. And other dual grid methods do this differently, but in the finite volume world with going off solvers, it makes sense to kind of think about a cross section on each of the four sides and evaluate your fluxes there. So if you have a levee or something intersecting the middle of the cell, you might completely miss that feature. And so, in fact, this is something that Ben and I have interacted with before in the past, and he's published papers on this issue. So we've came up with a method just to take available levee polyline data, which is shown in red. So imagine you've got a network of channels, and each of those channels has a levee on the bank of the channel. So that's a high point, and unless you resolve that levee, you're gonna not predict the onset of flooding at the right time. So what we've been trying to do is come up with a method where you could input polyline data, and then the idea is that you would shift the position of your levee to the nearest edge of the grid. And so the white line represents where we're effectively enforcing the blockage effects of the levee. So it's not precisely the same location as where the levee is located. But the smaller the upscale factor you use, the better job you kind of approximate that levee. And as you go to coarser and coarser grids, then your approximational levee gets more and more coarse as well. But what you're prioritizing here is sort of the containment of water within a flood channel and not having any openings or leaks where you would get sort of artificial flooding or a model predicting flooding before it really should predict the onset of flooding. So that's one of the things we do for urban areas in other areas, even rural areas, to try to get flood models to be more accurate. The other thing we focus on is sort of hydro conditioning of the digital elevation model to make sure we have, important flow paths resolved as open channels. So this is an interchange in not far from the UCI campus. This is the interchange of the 73 freeway and the 55 freeway in Southern California. But there's an open channel that's probably like maybe 100 feet wide here that runs underneath this interchange out over here in a big box culvert. It's not unusual to have tons of box culverts all over Southern California. That some of these things go for like miles underneath neighborhoods. And clearly, if you're just relying on LiDAR data to represent your flooding, and the water's going to come along here, it's going to stop. There's nowhere to go. It's going to pool. It's going to have to move its overland flow over this, and then maybe it'll collect over here afterwards. And that's really not representative of the actual flooding. So what we've been doing is working with methods of acquiring like GIS shape files of channel center lines, channel width information, and then burning open channels into the DEM where we know there's a flow pathway. Another thing that can come up is that freeways, overpasses, sometimes, depending on how the LiDAR is processed, will show like the elevation of the top of the freeway deck here and not the elevation of the ground underneath it. And if there was water coming down this roadway, it's going to just keep going down this roadway physically. But if the LiDAR shows a blockage effect there, then that's not going to capture that. So basically just to summarize, like our recipe for modeling urban areas has been to start with like high quality LiDAR data. We found 3 meters kind of works reasonably well most of the time. We hydro conditioned the DEM to represent sort of deal with roadway flow pathways. We modify the DEM to represent subsurface pipes, culverts, using like drainage network polyline data. And then, oh, this is updated. We've actually for the for that paper where we compared against the first treat data, we added these 166,000 inlets across LA County and did that as well. But for earlier work, we were thinking about these compound flood risks facing Los Angeles, and there's fluvial risks from runoff from the mountains into these main stem flood channels. There's pluvial risks from intense rainfall across the landscape. There's coastal risks from you can see high tides and waves along the coast. We've also been studying like the clogging of channels under a different grant, with sediment and debris and how that affects flooding. And something else that's, I think, worth noting is that, channel condition changes over time. How the geometry of a channel as it was built may be different than the geometry of the channel, at any given time. And when in our study, we were using a LiDAR survey that was somewhat recent of the topography, which captures channels in various conditions. Some channels that have recently been cleaned, some channels that might be clogging with sediment and vegetation. And flood control agencies, have a schedule to try to get out there and maintain their flood infrastructure. But the flood infrastructure may not be at capacity when it rains, right? And so models that assume everything's in an as-built conditions would necessarily overestimate the sort of the level of protection that infrastructure provides. So then using those approaches, we built this model of Los Angeles County, which was published in 2022, and then documenting the amount of risk that sort of was present in Los Angeles County. And one of the things this model predicted was that these main stem flood channels were undersized to contain a 1% annual chance event. Both the Los Angeles River, there's a Dominguez channel, which comes over here, and we predicted some overtopping. There was a Compton Creek channel, which is over here. Also, some actually Compton Creek is over in this one. So when we first ran our models and saw that these channels were overtopping with a 1% annual chance event, it caused us to pause and say, wait a minute, like I thought these levees were all rated for like a 100-year event and would provide protection. And so we started doing more digging, and sure enough, like the Army Corps had done a study of the LA River and documented that it was undersized in places to contain a 1% annual chance event. LA County Department of Public Works had done separate studies for some of these, like Compton Creek and Dominguez Channel, independently concluded that those channels were undersized to contain a 1% annual chance event. So in our supplementary information of that paper, we kind of showed one of those studies. It was this Army Corps HEC-RAS model. Army Corps built a combined 1D, 2D HEC-RAS model. It was interesting. They used 1D in the channel, and then they used 2D in the overbank areas. And this was their estimate of like the flooding that could happen along a reach. They tend to do reach scale models. So this was along a reach of the Los Angeles River. And so we tried to build a PRIMo model for the same stretch of the river and just see like how well the models, were they telling the same story or not. Our model tended to predict a little bit less overtopping, but overtopping in different places. And this was a model at the 5th percentile of what the 100-year flow is in the 95th percentile. So that should bracket a pretty good range. In general, our model is a little on the drier side than their model. Bottom line is that, small errors in the heights of levees, like 20 centimeters, are well within, the possibility when you use different data sets like LiDAR versus as-built drawings or survey grade data, and you can get different answers of where water is going to go depending on model structure and data inputs and so on. That's just, we try to acknowledge some of the uncertainties there, but nevertheless, the main point was that our model is predicting overtopping of the main stem channels, which was supported by independently by other studies. And then we looked at like who's exposed to flooding, and we could look at like exposure by different hazard drivers, like people and property exposed to pluvial flood hazards versus fluvial versus coastal. Our model pointed out that like there's, well over 200,000 people exposed at the 1% annual chance level, which in the FEMA flood zones at the time were pointing to like around 20,000 people within a 1% annual chance hazard area. Um, and the FEMA maps hadn't been updated to account for the fact that the channels were undersized. And why are the channels undersized? Well, the flood peaks have gotten just bigger and bigger over time with land use change. So as land use changes, loss of, soft surfaces, more impervious surfaces, more runoff, and it's just been decade after decade, the flood peaks have been going up. I also want to make a point here about quantifying social inequalities, which is we published a paper in ASCE Open with kind of a recipe method for how you can use spatially distributed flood data and social data like census data to quantify inequalities in flood risk by different social measures. So one of the things that we found in our first LA study was that Black populations were disproportionately, exposed to flood risk. And we use to do the inequalities, we use a Gini index, which is, I won't go into details, but it's shown here in the bottom. And let's just walk through, like, this is basically total losses estimated for the region. And then basically based on the spatial distribution of those losses and where population density is and where different population fractions are located, you could sort of say, well, how do those flood losses fall across, different segments of the population? So the simulation I just showed you was what we call the most likely simulation, like the 50th percentile. And then you can see that there's the losses are falling, to a degree for Black communities, highest for Hispanic populations, smaller for Asian populations, and sort of also high for white populations. Okay, and so that's how the losses fall across those populations. But depending on how many people live there, that loss may be disproportionate or maybe proportional. And so these Lorenz curves kind of characterize whether the loss is proportional or disproportionate. And then that overall inequality is registered as a Gini index. So any Gini index greater than 1 points to a disproportionate loss for that social group. And so even though the Black sort of population loss was the smallest of certainly much smaller than Hispanic and white, they had the highest inequality in flood exposure. On the other hand, white communities were disproportionately underexposed to flood risk. And then that's for loss. If you just look at exposed people, like who's living in areas at risk of flooding, we did the same thing. And there, like the inequality for Black communities was especially high, and the inequalities for white communities was especially low, and Hispanic and Asian were more middle of the road. So then we said, well, what if we, what's a good solution to solve this problem? And you'd like to be able to say, look, if we invest in intervention A or intervention B, should we raise levees? Should we invest in green infrastructure? Should we widen channels? How would that change exposure? How would that change inequalities? So we have this mitigation scenario where we just, for the purpose of illustrating the method, said, well, what if you raise levees, all throughout the system? And then if you raise levees, you can see that by this orange bar here, that flood exposure goes down for everybody. So think, well, that seems like a great solution. Interestingly, though, the inequality in exposure goes up for Black populations, and it gets even in white populations are even further less exposed. So you can end up having like quantitative metrics that inform not just the overall benefits in terms of losses of dollars or losses, number of people that would be benefiting from an intervention, but you can also say, look, who's benefiting from those interventions? Is this an intervention that it's fair to everybody, or is this somehow unequally benefiting different social groups? And so this paper kind of lays that out. We also, I think ran our method in to reproduce Harvey, and check my time here, and there we probably people in the room are much more familiar with the event than me, but there was a number of different gauge records and high water marks that were available to evaluate the model. So we ran a model with both um, forecast precipitation data that was available from like one of the forecast centers. It was like a 6-hourly forecast of flood precipitation depth. We also ran the model with a hourly hindcasted NOAA stage 4 precipitation data, and kind of compared how well the model could reproduce an event like this. One of the lessons there was that when we first ran the model with just the LiDAR survey, we found that the agreement was okay but not great, and it really pushed us to look at the bathymetry more closely. And we ended up doing like a calibration of the model for low flows, calibration of the bathymetry. So you imagine along all these bayous and channels, there's areas that are permanently inundated, and so data on how deep those channels are wasn't available to us. And so we found that by sort of looking at low flows and reproducing low flows, we could sort of calibrate those Thalweg elevations to capture the low flows better, and then we did a better job predicting the high flows. So this graphic here just shows a lot of different gauge records across the region, and this was like I think we ran it for like a 4 or 5 day, 6-day simulation, something like that. And I think on the CPUs, the way we had it set it up, this would run, in like 4 or 5 hours, something like that, and for a 4 or 5 day simulation. But in the central areas, the black line was the observations. The red line was the simulation with hindcasted rainfall. And then the green curve was a simulation with forecasted rainfall. Because the forecasted rainfall was every 6 hours, you can see it's a much smoother signal. And when you have hourly rainfall data, you can start picking up some of the, changes, more sort of temporal fidelity there. And in many areas, we did okay. I think there's some of the mean absolute errors were okay, but other, like up in these regions here, there was flow coming from outside our model domain, and we did a really lousy job capturing the flow because there's just flows we didn't have information on, like how much was coming from these other areas. But the message was that like bathy data is important, just even in high water events, trying to get if you want to get the flood stages right, getting the Thalweg elevations accurately estimated, and you're probably all over that now as an issue. But if you want get more information about statistics of the model in terms of a application in Texas, I mean, I think this paper certainly can help you there. Like this is a report, a table on sort of the quantitative metrics of performance. So if we look at peak stage at the gauges, the hindcasted model was giving a mean absolute error of like 63 centimeters across dozens of gauges there. The forecasted model at the same upscale factor of 10 was a little bit less accurate, obviously, because the information about the precip wasn't as strong. And then I think we also had a comparison to high water marks. There was like 220 high water mark, and again, like the hindcast model was coming in with a mean absolute error of like 69 centimeters, and the forecast model is a little less accurate. That was kind of a lesson there. And now just what caught all of your attention, I think, was this paper that came out where we compared against the First Street data. So how are we doing there? How are these comparing? And so the one difference from the model I showed you earlier, the first LA study, we didn't include all those storm drains. And for this study, we introduced a second model we called PRIMo drain, which had like those street drains. And we took the street drain flows and estimated them based on a Weir equation or orifice equation of water just going into the ground at the location of those drains. And we used the calibrated discharge coefficient that we had gotten from the Baldwin Hill study. So the kind of information we needed to do that work is kind of nicely summarized here. I thought I'd pull this graphic up. So you have your flood hazard data, you have your population density data. So where are people living? You have your property value data, um, which is parcel. We got this from the assessor's office. So this is like assessed values. It's not market rates per se, but assessed data. And then there's a number of different social indicators that we use for this study, which was the percent of the population Hispanic, the percent population that's white, percent that's Black, and percent that's disadvantaged, as measured by a index we introduced called the Neighborhood Disadvantage Index, which it's different from like social vulnerability index because it doesn't consider race or ethnicity. It's strictly like socioeconomic measure of disadvantage. So one thing I want to draw your attention to is that you can see that the Black populations are concentrated in the southern, maybe southwestern part of Los Angeles County. So Los Angeles River is coming down this area, and you can see that this is an area where Black populations are concentrated. Meanwhile, white populations are concentrated in coastal areas and in areas tend to be with more relief. So you'll see in upper elevation areas and in coastal areas, greater white populations. And then the Hispanic populations tend to be, very central in the region. So clearly, like inequalities in flooding will result from more or less flooding in areas where a social group has its population density concentrated. So with that, I thought I'd just do a brief overview of model differences. So in PRIMo, we use this dual grid model, as I've shown you, where we use the 3-meter resolution topo data to resolve fluxes and then do the integration at 30 meters. In the First Street data, they use a 30-meter digital elevation model for routing. And then after the routing's done, they downscale to 3-meter for mapping purposes. But the 3-meter data is not used for routing. Okay. For the pluvial forcing, we both use the same information. We pulled out precipitation intensity data from a NOAA Atlas 14, spatially distributed rainfall intensity data. For fluvial forcing, we had access to like over 50 local gauge records from Los Angeles County Department of Public Works and Orange County Public Works and the First Street tends to kind of have access to a limited set of gauges. They're not crystal clear on which gauges they use for any particular area, and they have some sort of regionalization method that they use. So I think the bottom line is that if you're trying to do flood modeling nationally, it's really hard to like have the same level of local information everywhere. So there's differences in the fluvial forcing. And then on the infrastructure side, we start with that DEM and we hydro condition for culverts. We try to sharpen the levees. We counted for the storm drain inlets. It's kind of hard to understand exactly how First Street does infrastructure. They refer to some masking techniques where they mask areas out if those areas flood at a level that's more frequent than the levees are rated. So I think they have a lot of sort of checks they do. If they think the levee is containing a flow, then they'll try to mask that out and not. So and you can try to read our Joe Schubert, tried really hard to write up the First Street methods based on a bunch of different sources. And you can find that in our paper. But this graphic here shows the areas where the models agree, which is the dark blue. And unfortunately, there's not very many areas where the models are in agreement. And then these orange areas are areas where the First Street data predicts flooding and we do not predict flooding. And then the pink areas are areas where we predict flooding and the First Street does not predict flooding. So the highest level, the sort of assessment is that we're predicting channel overtopping in the lower areas. These lower areas are showing to be pooling with water because the channel's overtopped with flooding. And so we tend to predict more flooding in these lowland areas along main stem channels, where historically, those are the historical floodplains. Those are the more disadvantaged areas. The First Street data tends to predict a lot more flooding in areas with higher relief. So these high relief areas, tend to show much wider flooding. If you get into the mountains, like mountain canyons are mapped out as, bottoms of canyons are all mapped out as being areas where there's flooding. We did some statistics on how the models compare for different regions. Overall, like the model agreement index, which is a measure of how much overlap there is like around 24% between the two methods. But the bias kind of predicts whether there's more or less flooding predicted by more flooding predicted by First Street versus PRIMo. And the foothill areas, so that would be like up in this box here, they're predicting like 3 times more flooding than we predicted. And what we called like this riverside area, you can see that they're predicting about half as much flooding as we're predicting. So that basically sums up the difference between the models. They're predicting more flooding in high relief areas, and we're predicting more flooding along main stem flood channels. If you look at the across all the 3 models, we had the First Street, the PRIMo, and then the PRIMo drain. Like the number of people exposed at the county scale was actually not that different across the 3 models. So if you just want to know how many people are at risk in this county, I think the First Street data seems to be giving a number which is within a factor of certainly within our PRIMo model, a factor of like 25%, 30%. But if you want to know like which municipalities within the county are most at risk, you can get a much different answer. So there's over 80 different municipalities inside of Los Angeles County. So what we did is we estimated how many people in each municipality would be exposed to flooding according to these 3 different models. And we can just look at this PRIMo versus First Street. And what you'll see is that like in some areas, First Street's predicting a lot of exposure for that municipality, but where PRIMo is predicting very little, and vice versa. So we can't. There's a statistic called the geometric mean relative error, which is kind of like a measure of the differences, and on average, basically that means that the municipal scale, the differences are a factor of 4 on average in number of people exposed in a municipality. And if you compared PRIMo drain to First Street, the differences are on average a factor of 7. And that's true for exposed property value too. So you can have a factor of 5, even a factor of 9, almost a factor of 10 difference in the amount of property exposed by municipality, depending on whether you're using one data source or the other. And another sort of striking result was that the social inequalities that you would predict using First Street data are markedly different than the social inequalities you would predict using the PRIMo data. And if we look at for exposed population, we look at sort of this Gini index again. The PRIMo models are suggesting that more disadvantaged people are disproportionately exposed, that Black communities are more disproportionately exposed, and that white communities are disproportionately underexposed to flooding. The First Street data is suggesting that disadvantaged people are disproportionately underexposed, that there's really no inequality for Black populations, and that Hispanic are underexposed and white are overexposed. And when it goes to property value, those things get even stronger. So the implications of the different data sources are profound. Depending on which data source is sort of used, you can get a much different estimate of who is most exposed in terms of social groups. So in general, just to sum things up today, flood inundation models are very sensitive to topographic data. Acceptable accuracy hinges upon the usual things like of a model: good topographic data, good foresting data, representation of flood infrastructure. We found that these dual grid models can support accurate, more fast response flood inundation modeling at regional scales. As I showed in that Baldwin Hills test case, there's not a whole lot lost going from up to upscale factor of 10, it seemed, in that Baldwin Hills test case. And another issue we raise in our paper is that the data are often inadequate for rigorous validation of flood inundation models. So we just don't systematically monitor extreme flooding within urban areas where that flooding happens. We have gauge records. Gauge records tell us, information that's valuable, but that's, the flooding within urban areas it's a long way away from a gauge. So, and I guess I'll point out that most large-scale flood inundation models are operating without detailed knowledge of topography and flood infrastructure. And I think that our work and the Bloomberg report really highlight these really understandable concerns about the lack of transparency in some of these climate data sets.